Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The year 1927 witnessed an extraordinary flowering of theoretical physics, a period of intense intellectual ferment, where the very foundations of our understanding of the universe were being radically reshaped. Central to this revolution was Werner Heisenberg's groundbreaking paper, Quantum Theoretical Reinterpretation of Kinematic and Mechanical Relations. This work, published in the journal Zeitschrift für Physik, presented a radical departure from classical physics, introducing concepts that would forever alter our perception of reality at the atomic and subatomic levels. To fully appreciate the paper's significance, we must first delve into the intellectual landscape from which it sprung. The early 20th century saw classical physics struggling under the weight of experimental observations that defied its established principles. The wave-particle duality of light, the photoelectric effect, and the anomalous behavior of atomic spectra all pointed to the inadequacy of Newtonian mechanics and Maxwell's electromagnetism in describing the microscopic world. These observations spurred intense theoretical activity, leading to the development of the old quantum theory, a collection of ad hoc rules and postulates that, while partially successful, lacked a coherent, fundamental framework. The Bohr model of the atom, for instance, introduced quantized energy levels but offered no explanation for their existence or the dynamics of the electrons within the atom. The stage was set for a more profound and mathematically rigorous theory. Heisenberg's work was profoundly influenced by the theoretical developments of the preceding years, most notably the matrix mechanics approach pioneered by himself, Max Born, and Pascual Jordan. This approach, born from Heisenberg's conceptual focus on observable quantities, represented a fundamental break from the classical picture of particles having definite trajectories and positions. This new formulation, guided by his work with Born and Jordan, utilized matrices to represent physical observables. Each physical quantity, like position or momentum, was described by a matrix. The dynamics, evolution of these quantities in time, became encoded in matrix operations. The rules of classical mechanics, such as the fundamental Poisson bracket relations for position and momentum, were replaced by analogous matrix algebraic relations. The core principles of matrix mechanics were already established. Born and Jordan's work on matrix mechanics had laid considerable groundwork. This theoretical method, while mathematically elegant, initially presented significant conceptual challenges. Its abstract nature and the unfamiliar formalism of matrices challenged physicists accustomed to the more intuitive language of differential equations and continuous trajectories. The work required a shift in perspective, moving away from a classical picture of particles' definite position and momentum at any given time. Heisenberg's 1927 paper built directly upon this foundation. It addressed the inherent limitations of the old quantum theory's attempts to reconcile classical concepts with quantum phenomena. Its primary focus was a reinterpretation of the kinematic and mechanical relations, the fundamental rules governing motion and interactions. His central insight was a radical re-evaluation of what the concept of a physical quantity actually meant at the quantum level. His argument centered on the inherent limitations in the simultaneous measurement of certain pairs of physical properties. Consider, for instance, the position and momentum of a particle. In classical mechanics, we assume that both these quantities can be determined with arbitrary precision at any given moment. Heisenberg's reinterpretation, stemming from the mathematical formalism of matrix mechanics, suggested that this was fundamentally incorrect. He showed that the act of observation itself inevitably disturbs the system, leading to a fundamental uncertainty in the simultaneous knowledge of these two properties. This led to the formulation of the famous uncertainty principle, the cornerstone of his 1927 paper. The uncertainty principle, as mathematically expressed, stated that the product of the uncertainties in a particle's position and momentum must always be greater than or equal to a constant value, Planck's constant divided by 4 pi. To be clear, this did not imply limitations with our instruments. Instead, uncertainties were intrinsic to the quantum world itself. The more precisely one determined a particle's position, the less precisely one could know its momentum, and vice versa. This was not a measurement problem, it was a fundamental property of nature. The position and momentum were related in a reciprocal. The uncertainty principle, which Heisenberg's paper introduced, wasn't merely a mathematical statement. It had profound philosophical and conceptual implications. It directly challenged the deterministic view of the universe that had dominated classical physics. Newtonian mechanics, in principle, allows for the precise prediction of a particle's future trajectory if its initial position and momentum are known. The uncertainty principle, however, argued that we cannot know both of these quantities with perfect accuracy. thus undermining the possibility of precise prediction. The universe, at its most fundamental level, was inherently probable. The beauty of this reinterpretation lay in its conceptual elegance and mathematical rigor. Heisenberg replaced the notion of definite trajectories with a probabilistic description of particle behavior. Instead of knowing a particle's exact position and momentum, one could only calculate the probability of finding that particle at a particular location with a particular momentum. He established a direct relationship between the wave and the particle aspects of matter. The wave nature of particles, as hinted at by the matrix mechanics, was fundamental to describing their behavior. The mathematical formalism employed in Heisenberg's paper was sophisticated for its time. It involved the use of matrices, the fundamental building blocks of his matrix mechanics. He developed concepts from the early work of Max Born and Wolfgang Pauli. Heisenberg's matrix-based approach presented the physical quantities as operators. These operators acted on abstract mathematical objects. These objects, later understood as wave functions, described the state of the quantum system. The dynamics, the time evolution of physical quantities, was governed by these operators. This complex mathematical structure showed a deep understanding of not only quantum mechanics but also the related mathematical frameworks. To drive home its significance, the immediate impact of Heisenberg's work was nothing short of revolutionary. It provided a coherent and consistent framework for understanding a wide range of previously puzzling experimental phenomena. One primary example was the explanation of atomic spectra. The matrix mechanics and the uncertainty principle allowed for the accurate calculation of the frequencies and intensities of light emitted by atoms, providing a profound understanding of the internal structure of matter. It also explained the stability of atoms, resolving the issue of why orbiting electrons did not radiate energy and spiral into the nucleus. Heisenberg's work provided the basis for understanding of chemical bonding. The impact of Heisenberg's work, however, extended far beyond the confines of theoretical physics. It ushered in an era of experimental exploration. The discovery of the uncertainty principle spurred the development of new experimental techniques and technologies. Physicists needed to challenge its boundaries, and this drove innovation. Experimentalists sought to test its limits, design more precise instruments and develop new measurement protocols. These advancements, in turn, further refined the theoretical understanding of quantum mechanics. Heisenberg's work directly influenced the development of quantum electrodynamics, solid-state physics, and nuclear physics, disciplines that now underpin many technological advancements. The immediate impact of his work became clear when Niels Bohr and others quickly adopted it and integrated it into their work. The rapid adoption by the scientific community showed the importance of the work. The scientific community quickly recognized its power. The legacy of Heisenberg's work persists. The uncertainty principle remains a cornerstone of quantum mechanics. This principle has been experimentally verified countless times. It has become an integral part of the education of physicists, chemists, and other scientists around the world. Is matrix mechanics, while initially challenging, has found its place in the standard framework of quantum mechanics. The 1927 paper was also not without its critics and alternative interpretations. Erwin Schrödinger developed wave mechanics, a different but equivalent formulation of quantum mechanics based on the concept of wave functions. Schrödinger's approach, while mathematically distinct from Heisenberg's matrix mechanics, produced identical results. This led to debates about the physical interpretation of the wave function and the nature of reality at the quantum level, issues that continue to be debated today. The probabilistic nature of quantum mechanics, as envisioned by Heisenberg, perplexed many. Albert Einstein, for example, famously expressed reservations about the completeness of quantum mechanics, stating his belief that God does not play dice. These debates highlight the profound philosophical implications of Heisenberg's work. The influence of Heisenberg's work on later generations of physicists is undeniable. Paul Dirac built upon Heisenberg's matrix mechanics, developing a relativistic quantum theory. This integrated quantum mechanics with special relativity. Dirac's work, in turn, led to the prediction of antimatter, profound extension of quantum theory. Concepts from Heisenberg's work continued to shape the development of quantum field theory, the standard model of particle physics, and other modern theoretical physics frameworks. Heisenberg's paper was also deeply influenced by interactions with other brilliant minds. His collaboration with Max Born and Pascual Jordan in developing matrix mechanics proved invaluable. Born's contributions to the statistical interpretation of the wave function played a crucial role in understanding the probabilistic nature of quantum mechanics. The discussions with Niels Bohr, particularly the development of the Copenhagen interpretation of quantum mechanics, were foundational. These discussions clarified the philosophical implications of the uncertainty principle and the measurement problem. Bohr provided a crucial framework for interpreting the matrix mechanics and the new quantum concepts. Equally significant was the influence of Heisenberg's work on others. His formulation of the uncertainty principle directly impacted the thinking of many of his contemporaries. Wolfgang Pauli, in his work on the exclusion principle, incorporated the probabilistic nature of quantum mechanics. Dirac's development of relativistic quantum mechanics and the development of quantum field theory built directly on the mathematical and conceptual frameworks established by Heisenberg. The impact of Heisenberg's work extended beyond the theoretical realm. His work provided a framework for understanding the behavior of matter at the atomic level. This understanding led to the development of new technologies. This is evident in the development of semiconductors. The study of these materials, key to modern electronics, relies heavily on the principles of quantum mechanics. Further technology in the field of materials science, the development of the laser, also depended directly on the insights of quantums. In conclusion, Werner Heisenberg's 1927 paper, Quantum Theoretical, the Interpretation of Kinematic and Mechanical Relations, was a landmark achievement. It fundamentally altered our understanding of the physical world. His work, born from the intellectual ferment of the early 20th century, offered a coherent framework from which to understand quantum phenomena. His formulation of the uncertainty principle challenged the deterministic worldview of classical physics, introducing a probabilistic view of reality. His matrix mechanics provided a new set of rules and tools to describe the behavior of matter at the atomic and subatomic levels. The paper's influence is still felt today, shaping the theoretical frameworks of modern physics, driving technological innovation, and prompting ongoing philosophical debates about the nature of reality. Heisenberg's genius, his boldness in questioning established order, and his mathematical prowess forever changed the course of science. His work stands as a testament to the power of human thought to unravel the mysteries of the universe.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.